Imagine sitting in a heavily fortified underground command bunker, staring at a state-of-the-art radar screen that shows absolutely nothing but clear skies. You are surrounded by the most advanced surface-to-air missile batteries on the planet, an integrated air defense network that cost billions of dollars to build. You feel completely secure in your subterranean fortress. Then, without a single warning siren, without a blip on the early warning systems, the roof of your bunker caves in under the weight of a 30,000-pound precision-guided bomb. That is not science fiction. That is the harsh reality of facing the United States Air Force B-2 Spirit stealth bomber. Welcome back to the channel, where we dissect the hardware, the history, and the brutal realities of modern warfare. Before we dive into the mechanics of the ultimate first strike weapon, I want to ask you a question. Do you think the era of stealth bombers is coming to an end with the rise of new quantum radars? Or is the flying wing still the undisputed king of the night sky? Let me know your thoughts in the comments below. And if you want to understand how wars are actually fought and won, make sure you hit that subscribe button. Now, let us strip away the classified tape and look at the anatomy of an apex predator. To understand why the B-2 exists, we have to go back to a time when the world was perpetually 5 minutes away from total nuclear annihilation. The late 1970s and early 1980s presented the Pentagon with a terrifying mathematical problem. The Soviet Union had spent decades building the densest, most lethal anti-aircraft network in human history. They were deploying the S-300 surface-to-air missile system, known to NATO as the SA-10 Grumble. This was a system that could track multiple targets, guide multiple missiles simultaneously, and swat traditional bombers out of the sky before they even crossed the Soviet border. The United States Air Force relied heavily on the legendary B-52 Stratofortress. The B-52 is a magnificent machine, a true workhorse of the strategic bomber fleet, but on a radar screen, it lights up like a massive aluminum barn flying at 30,000 feet. Planners at the Strategic Air Command ran the combat simulations, and the results were grim. In a conventional or nuclear first strike against the Soviet homeland, the casualty rates for American bomber crews would be catastrophic. We had seen this movie before. Look back at the summer of 1943, during the combined bomber offensive over Germany. The United States 8th Air Force sent unescorted B-17 flying fortresses deep into hostile territory to strike industrial targets like the ball-bearing plants at Schweinfurt. The prevailing theory was that heavily armed bombers flying in tight defensive formations could fight their way to the target. The theory was completely wrong. The Luftwaffe tore them to pieces. In one raid alone, we lost 60 bombers in a single day, with 600 highly trained airmen killed or captured. It was an unsustainable bloodbath that forced a complete halt to deep daylight raids until the P-51 Mustang arrived to provide escort. We learned a bitter lesson that you cannot win a war if your bombers are destroyed before dropping a single pound of ordnance. Fast forward to the Cold War. And the Air Force knew they could not send B-52s into the teeth of the Soviet air defense network without suffering a modern-day Schweinfurt. They tried flying low and fast to hide in the radar clutter of the terrain with the B-1 Lancer. But the Soviets developed look-down, shoot-down radars for their interceptor aircraft, making low-altitude penetration virtually suicidal. The Air Force had previously tried building a supersonic high-altitude bomber, the B-70 Valkyrie, hoping to simply outrun the missiles. But surface-to-air missile technology advanced much faster than jet engines. A missile will always be faster than a bomber. So if you cannot fight your way in, if you cannot hide in the dirt, and if you cannot outrun the threat, you are left with only one tactical solution. You have to become invisible. This realization birthed the Advanced Technology Bomber Program. The mandate was simple to say, but incredibly difficult to execute. The military needed a strategic bomber capable of carrying massive payloads from the continental United States to Moscow, completely undetected by Soviet radar. Two defense giants, Lockheed and Northrop, entered the ring. Lockheed had just revolutionized tactical aviation with the Have Blue project, which eventually became the F-117 Nighthawk stealth fighter. Their approach to stealth relied on faceted angles, utilizing flat surfaces that scattered radar waves away from the receiver. It worked brilliantly for a small strike aircraft, but it made the airframe aerodynamically unstable and severely limited its payload and unrefueled range. Northrop took a radically different path. They looked back at the pioneering work of their founder, Jack Northrop, who had obsessed over the flying wing concept in the 1940s. The YB-49 flying wing was an aerodynamic marvel, eliminating the fuselage and tail section to drastically reduce drag. It crashed and was cancelled because human pilots simply could not manually control such an unstable design without modern computers. But by the 1980s, fly-by-wire computer systems had matured. Northrop engineers realized that a smooth, continuous flying wing was not only aerodynamically efficient for extreme range, but it was also the perfect shape to defeat radar. Let us talk about what stealth actually means on the battlefield, because it is widely misunderstood. It is not a magical cloaking device. Stealth is about reducing your radar cross-section, or RCS, to delay detection until it is too late for the enemy to react. When a radar dish sends out a pulse of electromagnetic energy, it bounces off an object and returns to the receiver. A B-52 has a radar cross-section of about 100 square meters. An F-15 Eagle fighter jet is about 5 square meters. The B-2 Spirit, despite having a wingspan of 172 feet, which is wider than a Boeing 767 airliner, has a radar cross-section roughly the size of a bumblebee. It achieves this through a combination of radical shape and highly classified materials. There are no vertical stabilizers to reflect radar energy. There are no hard angles. The smooth sweeping curves of the flying wing deflect radar energy away from the source. But shape is only half the battle. The aircraft is coated in radar-absorbent material, a highly specialized composite that literally absorbs electromagnetic energy and converts it into heat. Even the engines are hidden. The four General Electric F118 turbofan engines, each producing over 17,000 pounds of thrust, are buried deep inside the wing. The exhaust is routed through trenches on the top of the aircraft, mixing the hot exhaust gases with cold ambient air before it leaves the airframe. This masks the bomber's infrared signature from heat-seeking missiles and prevents contrails from forming at high altitudes. The engines do not have afterburners, because an afterburner creates a massive thermal plume that would light up satellite sensors in low Earth orbit. The aircraft operates at high subsonic speeds, around Mach 0.95, because flying supersonic creates friction that heats up the leading edges of the wings, destroying the stealth profile. This brings us to a critical question regarding the physics of flight. How do you steer a massive wing without a tail? If you have ever thrown a paper airplane without a vertical fin, you know it simply spins out of control. The B-2 solves this yaw control problem with split brake rudders on the trailing edges of the wings. To turn left, the speed brakes on the left wing open slightly, creating drag and pulling the nose in that direction. It is a brilliant engineering solution, but it creates a massive amount of aerodynamic instability. The B-2 is inherently unflyable by a human being. It relies on a quadruple redundant, fly-by-wire flight control system that makes thousands of micro-adjustments per second, just to keep the aircraft flying straight and level. If all four computers were to fail simultaneously, the aircraft would flip out of control in a fraction of a second. This level of technological complexity brings us to the industrial and logistical reality of operating the B-2 fleet. The United States only built 21 of these aircraft, and today 20 remain in service, all based at Whiteman Air Force Base in Missouri. The cost of a single B-2 is estimated at over $2 billion when factoring in research and development. That makes it the most expensive aircraft ever built in human history. Maintaining this fleet requires an industrial base that operates with surgical precision. A gap of 1/4 of an inch between two access panels on the skin of the bomber can create a radar reflection that compromises the entire mission. Ground crews spend hundreds of hours meticulously applying specialized radar-absorbent tape and putty to every seam and rivet before a combat mission. The aircraft must be housed in specialized climate-controlled hangars because the stealth coating is highly sensitive to moisture and extreme temperatures. It costs over $130,000 per flight hour to operate a B-2. Critics often point to this astronomical price tag and the high maintenance requirements as a fatal weakness. We must examine what that $2 billion actually buys you on the first night of a war. It buys you the ability to kick down the door of any nation on Earth. Let us compare the strategic strike doctrine of the B-2 against the modern anti-access area denial networks deployed by near-peer adversaries. The modern battlefield is saturated with overlapping layers of defense. You have early warning radars operating in the VHF and UHF bands, which can detect large anomalies in the sky from hundreds of miles away. You have high-frequency X-band radars that guide the actual interceptor missiles. You have combat air patrols of enemy fighter jets equipped with powerful phased array radars. For a conventional strike package to penetrate this airspace, you need a massive armada. You need electronic warfare aircraft like the EA-18G Growler to jam the enemy radars. You need fighter escorts to clear the skies of enemy interceptors. You need specialized aircraft firing anti-radiation missiles to destroy the surface-to-air missile sites. You need a fleet of aerial refueling tankers to support this massive package. Coordinating a strike package of 50 or 60 aircraft is a logistical nightmare, and it gives the enemy ample warning that an attack is coming. The B-2 changes the strategic math completely. It operates entirely alone. It does not need fighter escorts, because the fighters would only give away its position. It does not need electronic jamming aircraft because it relies on its own low observability. A single B-2 can take off from Missouri, fly across the globe with the help of stealthy aerial refueling, penetrate the most heavily defended airspace in the world, drop its payload, and return home. This brings us to the human element, which is often overlooked when discussing high-tech machinery. A typical B-2 combat mission lasts anywhere from 30 to 40 hours. There are only 2 pilots in the cockpit. The mission commander sits on the right, and the pilot sits on the left. The cockpit is about the size of a small walk-in closet. For 40 hours, these 2 officers must manage the aircraft, monitor the stealth signature, communicate with strategic command, and prepare for the strike. Behind the 2 ejection seats, there is a small flat space where one pilot can unroll a sleeping bag and take a nap while the other flies the plane. There is a small chemical toilet and a microwave to heat up meals. The physical and psychological endurance required to fly a 40-hour combat mission, knowing that a single mistake could result in being shot down over hostile territory, is absolutely staggering. We saw this capability proven during Operation Allied Force in 1999. B-2 bombers flew non-stop from Whiteman Air Force Base to the skies over Serbia, a round trip of over 30 hours. They dropped precision-guided munitions on critical command and control targets in Belgrade, and flew back to Missouri. They bypassed the Serbian air defenses completely. It was a stark contrast to the massive bombing raids of the past. During the Linebacker II operations in Vietnam in 1972, the United States sent waves of B-52s over Hanoi. We lost 15 B-52s to North Vietnamese surface-to-air missiles in just 11 days. The loss of life and the loss of strategic assets was a heavy price to pay. The B-2 was designed to ensure that we never have to pay that price again. Now let us look at the payload capacity. The B-2 can carry 40,000 pounds of ordnance in 2 internal weapons bays. But it is not just about the raw weight. It is about extreme precision. During the Gulf War in 1991, the F-117 stealth fighter proved the value of stealth and precision, but it could only carry 2 2,000-pound laser-guided bombs. It could hit 2 targets per sortie. A single B-2 Spirit can carry 80 independent 500-pound Joint Direct Attack munitions, or JDAMs. Each one of those bombs is GPS-guided and can be programmed to hit a separate target. One B-2 can fly over an enemy airfield and simultaneously destroy 80 individual aircraft shelters, radar sites, and fuel depots in a single pass. That is the equivalent firepower of an entire squadron of conventional strike aircraft, delivered by a single ghost in the night. The aircraft utilizes the AN/APQ-181 phased array radar, operating in the Ku band. This radar uses low probability of intercept modes, meaning it can sweep the ground to update the GPS targeting coordinates without setting off enemy radar warning receivers. But the most terrifying weapon in the B-2 conventional arsenal is the GBU-57 Massive Ordnance Penetrator, or MOP. This is a 30,000-pound bunker buster. It is 20 feet long and made of a specialized hardened steel alloy. It does not carry a massive explosive warhead relative to its size. Instead, it relies on sheer kinetic energy. When a B-2 drops a MOP from 40,000 feet, gravity accelerates 30,000 pounds of solid steel to supersonic terminal velocity. It strikes the Earth like a meteor, penetrating up to 60 feet of solid reinforced concrete or 200 feet of earth, before the delayed fuse detonates the warhead deep underground. It is specifically designed to destroy deeply buried command bunkers and subterranean nuclear facilities. The B-2 is the only aircraft in the United States inventory capable of carrying this weapon. This capability forces adversaries to spend billions of dollars digging deeper and building thicker concrete walls, tying up their economic resources in a futile attempt to hide from the sky. But the enemy is not standing still. Near-peer adversaries have studied the B-2 for decades. They are developing low-frequency radars that can theoretically detect the general area of a stealth bomber. They are networking their air defense systems to share data across vast distances. They are building faster, longer-range surface-to-air missiles. We must ask if a modern VHF radar can detect a B-2 from 100 miles away. Does that mean stealth is obsolete? The answer requires a deep understanding of radar physics. Detecting a stealth bomber is not the same as targeting it. A low-frequency radar might tell an enemy commander that there is an anomaly in a 20-square-mile grid. But a low-frequency radar cannot provide a weapons-grade lock. To guide a missile, you need a high-frequency X-band radar, which requires a much smaller radar cross-section to bounce off of. By the time the X-band radar can actually see the B-2 clearly enough to guide a missile, the bomber is already directly overhead, and the bombs are already falling. It is a high-stakes game of cat and mouse, played out at the speed of light in the electromagnetic spectrum. The B-2 relies on highly classified electronic support measures to passively detect enemy radar emissions. The pilots can see the threat rings on their displays. They know exactly where the enemy radars are looking, and they can adjust their flight path to thread the needle, flying through the gaps in radar coverage. It is a silent, invisible infiltration. As the geopolitical landscape shifts and the rhetoric between global superpowers heats up, The role of the B-2 becomes more critical than ever. It is the ultimate deterrent. It is the physical manifestation of the United States' ability to project decisive, overwhelming firepower anywhere on the globe, at any time, without warning. The strategic calculus of any adversary must account for the fact that their most prized assets, their deepest bunkers, and their most advanced radar systems can be erased from the map on the opening night of a conflict. The crews at Whiteman Air Force Base train relentlessly for this exact scenario. They practice the long-duration flights, the complex aerial refuelings in strict radio silence, and the precise timing required to put a bomb through a ventilation shaft from 8 miles up. The industrial base works around the clock to keep the stealth coatings pristine and the avionics updated. Every aspect of this weapon system is honed for one specific purpose, and that is the first strike. The moment the diplomatic channels fail and the order is given, the heavy hangar doors in Missouri slide open. The black wings roll out onto the tarmac under the cover of darkness. The engines spool up, producing a low, earth-shaking rumble. The aircraft rotates, lifts into the night sky, and retracts its landing gear. Within seconds, it vanishes from the local air traffic control radars. The mission has begun. The crew settles in for the long transit across the ocean, moving silently toward a heavily defended coastline, preparing to execute a strike that will blind the enemy and open the door for the rest of the armed forces to follow. Once that landing gear retracts and the B-2 Spirit slips into the stratosphere, the reality of the mission sets in for the two pilots sitting in a cockpit no larger than a walk-in closet. Cruising at 40,000 feet, the ambient temperature outside the cockpit glass plunges to minus 60 degrees Fahrenheit. At this altitude, the air is thin, and the aerodynamic margins for a flying wing are razor thin. The pilots are not just flying an airplane, they are managing a highly unstable aerodynamic profile while constantly monitoring their electromagnetic signature. The Defensive Management System, or DMS, is the digital nervous system of the bomber. It constantly scans the environment for enemy radar emissions, categorizing them by threat level, and displaying them on the multi-function displays. The pilots do not just fly a straight line to the target. They fly a mathematically calculated route designed to keep the lowest possible radar cross-section pointed at the most dangerous enemy radar sites. It is a three-dimensional game of chess played in total darkness, where a single navigational error can result in a catastrophic surface-to-air missile launch. We need to look closely at what happens inside the weapons bays during this transit, because the B-2 is not just a delivery vehicle for dumb iron. It is a highly integrated node in a complex kill web. The aircraft features two massive internal weapons bays, and how they are loaded dictates the entire tactical profile of the mission. For a standoff strike, the B-2 relies on the rotary launcher assembly. Imagine a massive, mechanized revolver cylinder loaded with cruise missiles instead of bullets. This launcher can carry 8 AGM-158 Joint Air-to-Surface Standoff Missiles, or JSMs. The JASM is a 2,000-pound class stealth cruise missile with a range of over 500 miles. Now, you might be asking yourself a logical question here. If the bomber is already invisible to enemy radar, why does it need to fire invisible missiles from 500 miles away? The answer lies in the sheer density of modern terminal point defenses. While the B-2 can bypass the long-range early warning radars, the actual high-value targets, like a subterranean nuclear enrichment facility or a hardened command bunker, are often surrounded by short-range, optically guided, and rapid-fire anti-aircraft artillery systems. Systems like the Russian-designed Panzer S-1 do not necessarily rely on long-range radar. They have electro-optical sensors and thermal imagers. If a B-2 flies directly over a heavily defended target at low altitude, a vigilant operator with night vision and a thermal camera might just catch a glimpse of the exhaust, plume, or the massive silhouette blocking out the stars. By launching stealthy cruise missiles from 500 miles out, the B-2 completely removes itself from the terminal threat ring. This brings us to a historical parallel that perfectly illustrates the psychological and strategic impact of the B-2. Think back to April 1942, just months after the devastating surprise attack on Pearl Harbor. The United States was on the defensive across the entire Pacific. To strike a psychological blow, Lieutenant Colonel Jimmy Doolittle led 16 B-25 Mitchell bombers off the flight deck of the aircraft carrier USS Hornet. It was an unprecedented, highly risky mission. Those bombers had to fly just above the waves to avoid detection, drop their payload on Tokyo, and then, because they could not land back on the carrier, crash land in China. The physical damage to Tokyo was minimal, but the psychological shock to the Japanese High Command was seismic. They believed their homeland was completely untouchable. The Doolittle raid shattered that illusion and forced Japan to pull vital fighter squadrons back to defend their home islands, altering the course of the Pacific War. The B-2 spirit provides that exact same strategic shock, but without the need for a one-way suicide mission. An adversary can build a mountain fortress thousands of miles inland, surround it with the most advanced surface-to-air missiles on Earth, and believe they are perfectly safe. The B-2 shatters that illusion by delivering massive firepower directly to their doorstep without a single warning siren, sounding until the bombs are already detonating. But this capability is not magic, and it is not without its severe vulnerabilities. Stealth technology is incredibly fragile. The original radar-absorbent material used on the B-2 was notoriously susceptible to weather. If the aircraft flew through a heavy rainstorm, the friction of the water droplets at 600 miles per hour could literally strip the radar-absorbent tape off the seams of the aircraft, drastically increasing its radar cross-section. The Air Force has since upgraded the fleet with alternate high-frequency material, which is applied more like a spray paint and cures into a hardened shell, making it much more durable in adverse weather. However, the B-2 still cannot hide from everything. It leaves a contrail at high altitudes, just like any other jet. If an enemy fighter patrol happens to be flying above the B-2 in daylight, they can see the condensation trail pointing right to the bomber. This is why the B-2 is almost exclusively a creature of the night. It relies on the cover of darkness to mask its visual signature. The pilots are equipped with a contrail detection system, a laser that shoots out the back of the aircraft to detect if ice crystals are forming in the exhaust. If the alarm goes off, the pilots must immediately change altitude to find drier air, a maneuver that can disrupt their carefully planned stealth routing. Let us recreate the operational reality of a first strike mission against a near-peer adversary. Imagine a rogue state has built a heavily fortified ballistic missile launch facility deep inside a granite mountain range. Intelligence indicates they are preparing to launch a preemptive strike. The diplomatic options are exhausted. The president gives the order. 2 B-2 bombers launch from Whiteman Air Force Base. At H-12 hours, somewhere over the vast empty expanse of the Pacific Ocean, the bombers must refuel. This is one of the most dangerous and stressful phases of the mission. They rendezvous with a KC-135 Stratotanker. They are operating under strict emission control, meaning total radio silence. The B-2 pilots and the boom operator in the tanker must coordinate the connection of a flying fuel pipe at 30,000 feet, in pitch-black darkness, flying at 500 miles per hour, using only specialized, shielded formation lights. A mid-air collision here means the loss of a $2 billion national asset and the failure of a strategic mission. Once the bombers take on over 100,000 pounds of jet fuel, they break away and continue toward the hostile coastline. At H-3 hours, the bombers enter the enemy air defense identification zone. The electromagnetic spectrum is incredibly hostile. The B-2's passive sensors light up as they detect massive VHF early warning radars sweeping the sky from the coastline. The pilots do not jam these radars. Jamming is loud. Jamming tells the enemy exactly where you are, even if they cannot get a weapons lock. Instead, the B-2 absorbs the radar energy. To understand the tactical brilliance of this, look at the opening night of Operation Desert Storm in 1991. To open a corridor for the non-stealthy strike aircraft to bomb Baghdad, the United States Army had to send a task force of AH-64 Apache helicopters. Flying at 50 feet off the desert floor in total darkness, to physically blow up Iraqi early warning radar sites with Hellfire missiles. It was a brilliant but highly dangerous brute force tactic. The B-2 does not need to blow up the early warning radars to enter the airspace. It simply slips through the gaps. The pilots watch their displays as the threat rings overlap. They navigate the aircraft through the valleys of radar coverage, banking gently to ensure the smooth, sweeping leading edge of the wing deflects the X-band tracking radars away from the source. At H-1 hour, the bombers are deep inside hostile territory. They are flying directly over enemy surface-to-air missile batteries. The tension in the cockpit is absolute. The pilots are breathing pure oxygen. Every instrument scan, every micro-adjustment of the throttle is critical. They are approaching the initial point, the exact geographic coordinate where they will begin their attack run. The target is the granite mountain concealing the missile silos. Standard cruise missiles will just bounce off the rock. This target requires the GBU-57 massive ordnance penetrator. The B-2 is carrying 2 of these 30,000-pound monsters. As they reach the drop zone, the bomber must execute the most vulnerable maneuver of its entire flight. It must open its bomb bay doors. When those massive doors snap open, the smooth, radar-deflecting belly of the B-2 is suddenly broken. The internal cavity of the weapons bay acts like a giant radar reflector. For a window of about 5 to 10 seconds, the B-2's radar cross-section spikes dramatically. Down below, on the screens of the enemy air defense operators, a massive blip suddenly flashes into existence directly overhead. Panic ensues in the enemy command center. The operators scramble to lock their targeting radars onto this sudden apparition. But it takes time for a surface-to-air missile system to acquire a target, calculate an intercept trajectory, and launch a missile. The B-2 crew knows exactly how much time they have. The targeting computer releases the 30,000-pound steel behemoth. The bomb drops clear of the aircraft. Instantly, the hydraulic actuators slam the bomb bay doors shut. The smooth belly of the flying wing is restored. On the enemy radar screens, the massive blip simply vanishes, leaving the operators staring at empty static. Meanwhile, gravity takes over. The massive ordnance penetrator accelerates toward the Earth. It is not a sleek, aerodynamic missile. It is a flying telephone pole made of hardened steel, guided by GPS fins on the tail. It crosses the sound barrier as it falls, from 40,000 feet. It strikes the granite mountain with the kinetic energy of a freight train. The hardened steel nose does not shatter. It burrows. It punches through 10, 20, 40 feet of solid rock, driving deep into the subterranean complex before the smart fuse detects the void of the underground bunker. Then, thousands of pounds of high explosives detonate in a confined space. The shockwave cannot expand outward, so it expands inward, instantly vaporizing the command center, the missile silos, and the personnel inside. The mountain literally bulges upward as a localized earthquake registers on seismographs hundreds of miles away. A massive plume of dust, pulverized rock, and superheated gas erupts from the ventilation shafts. The primary target is completely destroyed. The preemptive strike capability of the rogue state neutralized in a fraction of a second. But down in the valley, the enemy air defense network is now fully awake, their screens illuminated by the massive thermal bloom of the explosion. And they know exactly where the invisible bomber was just 10 seconds ago. The enemy radar operators are now frantically scanning the airspace directly above the smoking crater. They have a massive thermal signature from the blast, and they know the exact theoretical trajectory of the bomb that just annihilated their command bunker. Surface-to-air missile batteries, previously operating in passive standby mode, suddenly illuminate the night sky with millions of watts of electromagnetic energy. The powerful X-band engagement radars of advanced systems like the S-400 Triumph are desperately searching for a target. sweeping the heavens in a frantic attempt to achieve a weapons-grade lock. But the B-2 Spirit has already closed its weapons bay doors. In the 5 seconds it took for the enemy to realize they were under attack, the bomber restored its flawless aerodynamic profile. Its radar cross-section has instantly shrunk back from the size of a commercial airliner to the size of a bumblebee. The radar waves from the enraged defense network hit the smooth, sweeping curves of the flying wing and scatter harmlessly into the void of the stratosphere. Down in the subterranean bunkers that survived the initial strike, enemy commanders are screaming into their radios, demanding interceptor launches. But you have to ask yourself a fundamental question about modern warfare. Can a hypersonic missile, no matter how fast or how deadly, destroy a target it simply cannot see? The answer is a cold, mathematical no. The B-2 pilots do not panic. They do not hit the afterburners because they do not have them, and a massive thermal plume would be a death sentence. Instead, they rely on the cold, calculated physics of low observability. They execute a pre-planned egress route, banking gently to ensure their lowest possible radar signature is pointed precisely at the most dangerous emitting threats. They thread the needle through the chaos, leaving the enemy air defense network to blindly files at empty patches of sky. To truly understand the paradigm shift the B-2 represents in this exact moment of evasion, we have to look at the brutal evolution of American strategic survivability. On May 1, 1960, the CIA sent Francis Gary Powers deep into Soviet airspace in a U-2 spy plane. The prevailing doctrine at the time was that extreme altitude was the ultimate defense. The U-2 flew at 70,000 feet, higher than any Soviet interceptor could reach. But the Soviets had secretly upgraded their SA-2 guideline surface-to-air missiles. They fired a barrage of them, and one detonated near Powers' aircraft, tearing the fragile glider apart and sparking a massive international incident. The United States learned that altitude alone was no longer a shield. We pivoted to extreme speed, developing the SR-71 Blackbird, which could fly at Mach 3.2 and simply outrun the missiles. But by the 1980s, interceptor missiles were pushing Mach 5 and Mach 6. Speed was no longer enough. The B-2 was born from the realization that if you cannot fly over the threat, and you cannot outrun the threat, you must become a ghost. The B-2 does not defeat the enemy with kinetic energy during its escape. It defeats them by completely shattering their O-Day loop. The O-Day loop, a concept developed by United States Air Force Colonel John Boyd, stands for observe, orient, decide and act. It is the fundamental cycle of all combat. By denying the enemy the ability to observe the bomber on radar, the B-2 prevents them from orienting their defenses, deciding on an intercept vector, and acting on a launch command. The enemy is paralyzed in a state of perpetual confusion, fighting a phantom that strikes with devastating kinetic force and then simply vanishes. While the bomber makes its silent escape over the hostile coastline, the multi-dimensional nature of modern American warfare kicks into high gear in low Earth orbit. The B-2 does not operate in a vacuum. Its strike is intimately tied to the National Reconnaissance Office and the sprawling intelligence apparatus of the United States. Within minutes of the massive ordnance penetrator detonating, highly classified keyhole satellites, utilizing advanced synthetic aperture radar and electro-optical sensors, are already passing over the target area. They are cutting through the dust and smoke to conduct Rapid Battle Damage Assessment, or BDA. This data is beamed securely back to the Pentagon and the subterranean command centers of the Strategic Command. The President and the Joint Chiefs of Staff do not have to wait days for a spy plane to take photographs. They know almost instantly if the rogue state's nuclear enrichment facility has been successfully vaporized. If the BDA shows that a secondary bunker survived, the B-2, still loitering hundreds of miles away in stealth mode, can receive updated GPS coordinates via its secure, low probability of intercept satellite data link. The pilots can reprogram their remaining munitions on the fly and turn back for a second pass. This level of integrated, real-time command and control is what separates a localized airstrike from a strategic decapitation campaign. But the strategic brilliance of the B-2 comes with an agonizing logistical and human toll that is rarely discussed in the glossy defense brochures. The moment the bomber crosses back into friendly airspace, the adrenaline of the combat drop begins to fade, and the brutal reality of human physiology sets in. These two pilots have been strapped into ejection seats for over 20 hours. They have navigated through hostile airspace, executed a precision strike, and evaded the most lethal air defenses on the planet. Now, they have to fly the aircraft for another 15 hours just to get home. Fatigue is the silent enemy that has killed more aviators than enemy fire. The Air Force meticulously manages this human element. The pilots are trained in specialized sleep cycles. They consume carefully measured rations. In extreme circumstances, they are authorized to use regulated stimulants, known in the military community as go pills, to maintain absolute focus during critical phases like mid-air refueling. The journey back to Whiteman Air Force Base in Missouri is a grueling marathon of endurance. It highlights a critical vulnerability in the B-2 program, which is its absolute reliance on a massive, highly centralized logistical tail. Let us compare the logistical footprint of the B-2 Spirit to another monumental American engineering effort, the Apollo program. When NASA sent men to the moon, the Saturn V rocket was the tip of the spear, but it required hundreds of thousands of engineers, specialized climate-controlled assembly buildings, and a nationwide supply chain to function. The B-2 operates on a similar principle of centralized, hyper-specialized support. Unlike a rugged F-15 Strike Eagle that can operate out of a dusty forward operating base in the Middle East, with a toolbox and a generator, the B-2 requires a pristine environment. Its stealth coating is a highly sensitive composite matrix. If a B-2 is forward deployed to a base like Diego Garcia in the Indian Ocean or Andersen Air Force Base in Guam, it cannot just sit on the tarmac baking in the tropical sun or enduring corrosive salt air. The Air Force had to design and build specialized, Deployable climate-controlled hangars, known as B-2 shelter systems. These are massive, clamshell structures that provide the exact humidity and temperature control required to keep the radar-absorbent materials from degrading. When the bomber finally touches down in Missouri after a 40-hour combat sortie, it does not just park on the flight line. It is immediately towed into a specialized dock where maintenance crews swarm the airframe. They use specialized diagnostic lasers to scan the entire surface of the aircraft, looking for microscopic scratches or delamination in the stealth coating. Every seam, every rivet, every access panel that was subjected to the friction of high-altitude flight must be meticulously inspected, retaped, and recoated with radar-absorbent putty. The putty must cure under precise environmental conditions before the aircraft is stealthy again. This intense maintenance cycle means that out of a fleet of 20 aircraft, only a handful are fully mission-capable at any given moment. This brings us to the inevitable economic and political debate surrounding the flying wing. Critics have spent decades pointing out that a $2 billion bomber that costs over $130,000 per flight hour is an unsustainable drain on the defense budget. They argue that in an era of asymmetric warfare, fighting insurgents with low-tech weapons, a stealth bomber is a relic of the Cold War. But this perspective fundamentally misunderstands the political economics of strategic deterrence. Is a $2 billion bomber too expensive, or is a $1 trillion war too costly to risk? When you look at the geopolitical chessboard, the B-2 is actually a highly cost-effective tool of diplomacy. Consider the concept of gunboat diplomacy utilized by President Theodore Roosevelt in 1907. He sent the Great White Fleet, a massive armada of United States Navy battleships, on a 14-month voyage around the globe. The purpose was not to start a war, but to project immense American industrial and military power, forcing adversaries to rethink their aggressive postures. Today, the President of the United States does not need to send a fleet that takes months to arrive. He possesses bomber diplomacy. If a near-peer adversary begins massing troops on a border or threatening a vital shipping lane, the Pentagon does not necessarily have to deploy an entire carrier strike group, which puts 5,000 American sailors at risk. The Air Force can simply launch a pair of B-2 bombers from Missouri, fly them non-stop to the region, drop a few inert training bombs on a testing range in full view of enemy radar, and fly home. The political message is deafening. It tells the adversary that the United States can reach out and touch their most highly valued, deeply buried assets at any moment, and there is absolutely nothing their air defense networks can do to stop it. This psychological leverage is worth far more than the $2 billion price tag of the airframe. As we look toward the future of aerial warfare, the B-2 spirit is slowly approaching the twilight of its operational life. The airspace is becoming more contested. Adversaries are heavily investing in quantum radar technologies, artificial intelligence-driven air defense networks, and low-frequency VHF arrays designed specifically to hunt stealth aircraft. The United States Air Force recognizes this shifting dynamic, which is why the B-21 radar is currently undergoing flight testing. The radar looks very similar to the Spirit, utilizing the same proven flying wing concept, but it is smaller, heavily reliant on open architecture software, and designed to be much easier to maintain. The B-2 was the pioneer, the bleeding-edge prototype of deep strike stealth that had to overcome insurmountable engineering hurdles. It proved that a massive, subsonic wing could penetrate the most hostile environments on Earth and deliver devastating payloads with pinpoint accuracy. Until the B-21 fully comes online and assumes the mantle, the 20 black wings sitting in the hangars of Whiteman Air Force Base remain the ultimate insurance policy for the American homeland. They are the apex predators of the night sky, a masterpiece of aerospace engineering born from the paranoia of the Cold War and refined in the precision strike era of the 21st century. War is ultimately a brutal calculation of violence, a mathematical equation where survivability is weighed against destructive capability. The B-2 Spirit tipped those scales completely in favor of the offensive, proving that true power does not always roar into battle with afterburners blazing, but sometimes slips through the darkness in total silence. I want to turn it over to you, the viewer, to analyze the strategic realities we have decoded today. Which element of the B-2 Spirit do you think is its most critical vulnerability in a potential future conflict against a near-peer adversary? Is it A, the extreme logistical and maintenance requirements that keep the aircraft tied to specialized hangars on the ground? Is it B, the rapid rise of advanced low-frequency detection networks and quantum radars threatening to strip away its invisibility? Or is it C, the physical and psychological fatigue of the two-man crew forced to manually manage an unstable flying wing during a 40-hour combat mission? Drop your answer and your tactical reasoning in the comments below.